Okay, welcome to the first video for the AP series, AP Physics 1 exclusive. This is not part of the regular further mechanics curriculum, it's fluids. I wanted to address that first. There's other parts in the AP Physics curriculum that are not in further mechanics, such as waves. I'm probably making videos on those as well. But let's get started with fluids because I think there is something here that every student of mechanics should know and understand. I'm probably not going to touch the chemistry and some of those other aspects that come in when you go into fluids, and neither will we get into the details of fluid dynamics. We will try and understand the principles of force and energy as it relates to fluids and how that affects other objects. We'll get started with our very first idea is to understand pressure, right? So I will define that, and hopefully you have a fair intuition by saying that if I have a particular force and if I apply that force over a large surface area, the effect that you feel is rather mild. But if I bring all of that force and concentrate it into a very, very small surface area, then you kind of feel something more effective and something becomes a little more, you feel it stronger, right? And that's in some way the basis of pressure. But when we come to fluids, we have the same idea. If you have a surface, let's just say some two-dimensional surface here, just randomly hanging there, then you have air, or assuming it's just the atmosphere of the room that I'm in, there is something that's holding this in reasonable form, and that's the pressure that air exerts on it. Likewise, our bodies, we're able to breathe and exhale and inhale thanks to air pressure, and our bodies being suited for air pressure. If we submerged ourselves in water neck deep and attempted to take a deep breath, the lung capacity would definitely be kind of lesser because you'd have ambient water pressure that's kind of squeezing, and obviously water is denser than air, and water pressure will be greater than air pressure. And as you go higher up into the Earth's atmosphere, the density of air there reduces, and therefore the ambient pressure also reduces. So imagine that as having a surface, and then all of the surrounding, material affecting, or rather the molecules of all of that just kind of bumping in, because they're fluids, then their molecules are just kind of moving around all the time, and they're constantly creating this effect. And if you kind of normalized all of them to the surface of this, if you normalize them perpendicular to the surface of this particular surface of the lamina, then you'll be able to come up with something that looks like a surface with a series of forces that are acting on it, and then if you brought them all together, combine them, it's this one force. And of course, this is a one-dimensional view of a two-dimensional surface which has an area A with a force F acting on it, will allow us to define pressure as force by area. I'm just doing a very, very simple high-level overview, but the intuition should be straightforward for you. If you've stepped in a swimming pool, or if you've gone in an airplane, you always understand when the captain says, in case of sudden depressurization. That's because an airplane is a pressurized cylinder high up in the atmosphere where the pressure is not suitable for human beings to breathe. You would just not have enough air, and of course your own blood vessels, your heart's pumping blood at a higher pressure, and the body will not be able to take the lower pressure outside of it, right? So same thing as if you attempted to create a vacuum right here, it would never be possible because air would just collapse, and you'd have a special chamber, and then you'd have a machine that exerts a lot of energy to suck out the air and create a vacuum. Why? Because ambient pressure is always very, very high. So this is a fundamental understanding when it comes to knowing what pressure is and how it relates to fluids. So getting any fluid, you're going to have pressure. Inside that fluid, assuming you were a little person swimming or diving inside, you'll be feeling a particular pressure, just as we are effectively now diving or existing in a fluid called, let's say, Earth's atmosphere, which is a combination of various gases, and we're diving in it very freely. Our bodies are used to it. The fish are used to the pressure in the water, and some aquatic organisms are used to higher pressures in the deeper trenches of water. So now let's use that segue and connect to. I explained earlier that if you have atmospheric pressure on the surface of the earth, and then as you went up, the density of the air, I'm using this alphabet rho, Greek alphabet rho, decreases, right? The density keeps going down as you go up, right? Therefore, the pressure is also going down, right? Likewise, and of course you could argue that that's because there's just more material here, and that's why the pressure is higher, right? There's much less air, the density is low, right? But now let's look at it the other way. If I was going to use this example and say, if I came into a water body and said, hey, this is the surface of the water body, and as I went down, the density of the water does not change. Raw water does not change. You could argue that there is a very tiny variation because of the compression effect, but typical fluids are liquids are not compressible. Fluids, on the other hand, because gases are also part of fluids, gases are easier to compress. You could compress water too, but that would be take a lot of energy, right? So if you came down, but the pressure increases. So why does that happen? Probably the way to visualize this and get the fundamental idea right is assume you have a, just for the sake of visualizing this, let's just say we have a, how do I draw this? Maybe the easier way to do this is maybe use another color. Maybe the easier way to do this is a section like that, and assume this is on the surface of this is the surface, right? And then if this height or depth, let me just say it's the depth, sounds better. If that's the depth, right at that depth, what's happening? You could say that, hey, there's the same amount of water molecules adding their little pressure by the collisions that they create, like I explained with air molecules around us that's creating this pressure. But if you were to look up, you'd notice that there is a big column of water here, and it's got a particular weight. Let's just take this column of water out for a moment and take a look at it. Right, what you'll see is you'll find this solid block of water. It has, let's say this cross-sectional area here is A, same as that. We did say that this is D, it's depth. My color's all messed up today. D is depth. Its volume then becomes B is equal to AD. If you know its density, we know the density of water, rho. If you know volume and you know density, then mass is nothing but, actually mass divided by volume gives you density. So I will now say its mass M is equal to rho AD, right? So I multiply volume with density, I should get the mass, and then it's evident to us that if you have a block of that size, acceleration due to gravity, a force is equal to rho a d g. This is like the real force acting on top of this. If you look at this equation here, and I want to define pressure, which is force per, let's write that down here, divided by A. What does that become? That becomes rho, density of water is roughly constant, acceleration due to gravity is constant. I'll keep the depth of water d there. So you can see that pressure is, the deeper you go, the pressure is higher, right? So the deeper you go in water, higher the pressure. There is no correlation to the volume of water, there is no correlation to any other. The only thing that is really correlated to here is, depending on which planet you are on Earth, there is no, this G doesn't change, so that's fairly. Rho, which is the density of water, right? Obviously salt water, different. If you have pure distilled water, be slightly less dense, but that is what makes pressure up. And obviously any other liquid, if it's oil, less dense than water, but the property of the liquid, this doesn't change much as long as you're on this planet. And then it's just the depth. So the deeper you go into water, the higher the pressure. Explains why submarines get, have a maximum depth beyond which they call it, I think they call it a crush depth or something, when they know that they're not supposed to get beyond there. But there are aquatic organisms down in the Marianas Trench, they've evolved to live in that pressure too. So just as an example, so the important idea to remember when we do fluids is that understand pressure as force by area, understand how that intuitively comes into explaining this. And I will now take that idea and build it into a concept of buoyancy and the buoyant force. I remember the spelling. Buoyancy. Okay? How do I bring that forward? Let me use the same picture and now try to explain this by saying, if I took a piece of iron and just let it sit there, what might happen to this block of iron if I just, let's say, there's this big chunk of iron, just sits there. It has a particular density. It's going to meet the water. Maybe let's just say I set it into the water, like right there. Okay. Let's get a try and make a little three-dimensional image of that. So there's water somewhere along that. There's water there, there's water here, so this is sort of the surface of the water. And let's say that has a volume V, right? I'm just going to say volume V. Should not use that, use uppercase V. Imagine that much of volume, there was water, and that water is now not there, iron's taken it. If water was to attempt to fight with iron and say, oh, that's my space, let me have it, and if water wanted to come back and say, sorry iron, you gotta move out, and push it out, iron would win, because given the same volume, we know that there is more mass in iron simply because its density is higher, it's a heavier element, substantially more dense than water, and therefore it would have its way and it would squeeze the water And of course, water being fluid would move aside and then come on top of it, and it would sink in because it has mass, and mg is the force that acts, and it basically takes it in. Similar to a solid object that just freely falls in our atmosphere, it's basically diving through air. That piece of iron would dive through water. Now, what if I made this into a very, very hollow block of iron where its total volume existed, but it was not massive? So yes, it's dense, but it's entirely hollow. So we know density of iron, but it's hollow. Think of it as a ship's hull, right? So you've got this big, huge ship, right? It's out there, it's massive, it's made of, let's say, metal, and it's big, but it's hollow inside, and therefore it's not as massive in the sense the total mass of that volume is not as high, and it meets it meets water, and water says, well, I'm going to fight for my space, come together, and water says, no, I don't have to move, you're not going to be able to push me. Why? Because suddenly the mg here is not sufficient to affect the weight of the water. That is, water doesn't have there's no hollow water. It could be a solid piece of water, which would be super heavy. If water was of this volume, it'd be ultra heavy because you could never make it hollow, and therefore water would win and the ship would stay afloat, right? We'll extend this. That effect that the liquid effectively, or the fluid, I should say, not liquid, the fluid has on this object, the force that it exerts upwards, and this is the, often called as the buoyant force. It is the force exerted by a fluid on an object that effectively keeps it afloat, or rather lifts it up. It's like a lifting force, and similar to a helium balloon or one of those gas balloons that you see kids play with, and one of the kids accidentally lets go and then it just flies away. It's just exactly the same thing. Helium is less dense than the air around us, and therefore air just says, sorry, my space, and helium keeps going up to a point where the density of the air and the helium matches, and of course temperature and cooling and all of that stuff, which we're not going to cover here. So that is what buoyancy is. Now let's just try to put some mathematics here just to see what happens, because ultimately we do want to get some math. So let's go back to this little block. We'll extend the block. I'll take all of this out. You know what this is. Let's just take a look at this. So we know the pressure there. So let's say that there's pressure here, right? And then let's say my let me just draw a piece of iron here now. This time, that's the piece of iron. It's a block. And right, and also has a little piece of iron in there, in the water. There's a depth there. So if you guessed it, let me just say that's D2. That's D1. We'll remove all that. A doesn't change. So we had a pressure here, and we have pressure here, right? And if you know, pressure is rho G D. On top would be 1 to rho G D2. And you can see here it's purely what does it translate to pressure? There's higher pressure here, and you could think of it as saying, hey, greater force acting here that wants to push it up, right? That's what it is. But how do you kind of say, okay, what's going on there? Well, you could say that the differential pressure, the delta P, is right, is what is causing it, times pressure times area, right, is the force, right? So whatever is this delta pressure, that's the force, and that's pushing it up. And remember, pressure is force by area, so force is that pressure times the area. We know the area, so we've got that. So this one's easy. So what else can we get? We can subtract P2 and 1, which will then give us density times G times D2 minus D1 times area. And you can see here, as I evolve this math out, and this is really the buoyant force, there is no mass function of this object here, because D1, rho 1, all of these belong to the fluid, right? Nothing really corresponding to this block here. And I should have ideally written all of this in blue, because there are no parameters that involve this block. Well, you could argue that maybe area does. Yes, area does. But even area, I mean, you could say, hey, this is the same as the area of the water or the fluid, right? If this is density of the fluid, I should say this is density of the fluid. You could say this is depth, D1, D2 are also, in some ways you could say they belong to the fluid because they're inside this fluid. This is definitely fluid. This is the pressure of the fluid, pressure of the fluid. Area, you could say, is also fluid. Of course, it has correlation to the object there. This is fluid, 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 also fluid. Which then would let me write the buoyant force as, and if you brought these two terms together, what I'm actually doing is creating a block of fluid, which is D2 minus D1 in size, and of area A, which means I'm rho fluid times volume fluid nothing to do with the object, it's really the volume. And guess what? Density and volume change would give me mass fluid times G. Voila, that's simply the weight of the fluid. So if you say an object is pushed with a buoyant force equal to the weight of the fluid, what happened? This is the fluid that this object displaced. That's Archimedes' principle. So really just the calculation of the buoyant force, but Archimedes stated it, however, whenever he stated it 2,000 years ago, 3,000, whenever, as a constant weight, right? He just said that take something and displace what, he displaced it with water or whatever, and then look at the weight of the water, and that's the force that the water pushes back with. Right, that's buoyancy. Hopefully clear to you. This is the concept. The calculations are very, very simple. It's really just simple mathematics, not even algebra, but just the conceptual understanding of what we're doing is valuable to know. Okay, that's buoyancy. That's done. Archimedes' principle done. Fluids, what else do we have? I think AP Physics 1 also requires you to know a concept called quantity of flow. I think they use, I think this is once it's done. They use Q as quantity of flow when it comes to a fluid, and I think it's stated as the volume by time, right? So it's like a rate of flow, but I think they call it a quantity of flow in the AP Physics 1 curriculum. It's basically rate of flow. Pretty intuitive, but what I want to do is the extension of this and where it's applied is assume you have a cylindrical pipe through which you have a fluid, liquid, whatever, flowing through. Cross-sectional area is A. Now what I can do is I can write the volume as, let's say, there is a distance, and let me just take a sectional view of this cylinder, and there is a distance D. Look at what happens. I can write this as area times distance divided by T. D by T, standard physics, is area times, observe carefully and please do not be confused, it's V as in velocity, not the big one for volume, right? So this is an interesting application when you come into liquids flowing through or gases flowing through pipes, right? And since the statement that it's quantity, which effectively is like saying it's the same amount of a liquid that flows at any time. So there's the idea of a steady streamline flow, and I'll try to state this because you assume that as a fluid goes through this pipe, fluid molecules are running around everywhere and they're bumping into the pipe and they're bumping against each other. But for the case of a lot of these calculations, the assumption is that they're all very obedient, very good, and they just move neatly in a straight line, with streamlined flow. But also, as observed at any given cross section, all of them will travel at the same velocity. So it's not like, hey, some of them move a little faster. Yeah, in reality, there's a lot of chaotic movement of particles or molecules in that in any given cross section. But for the purpose of these simple Newtonian mechanics calculations, you would just assume streamline and steady, meaning same speed, any cross section, and streamline meaning in the same along the same line, not one guy going this way, one guy going that way. Okay, so if you do that, you've got your A by V. What do they extend out of it? The extension out of it is an idea that says that, oh, wait a minute, now I have a reducer that's reducing the cross-sectional area of this pipe, and what happens to, well, effectively D, but written as V. So simple terms, if the quantity, because a liquid, and again, this is not for gases, for liquids which are incompressible, in the sense that you'd have to put in way too much pressure to get them to compress. So in the normal cases, they're incompressible, as is water, for example. Quantity flowing through at any given time does not change. So if there was water in all of this, and then I had this big pump here pushing out a bunch of, let's say, 10 cubic meters of water into this every minute, 10 cubic meters of water would have to come out of here every minute. There's no way anything else could happen. What goes in has to come out. So if you apply that logic, hopefully you get it. The quantity is the same. A changes, A reduces now. What happens? Velocity increases and the speed of flow increases. Okay? So effectively, to take this, let's say this volume of water now has to come out of here. The area is reduced, so it's basically a much longer you get a longer D2 because this area A2 and this is area A1 and let's say this is D1, so it's basically taking this cylinder of, say, depth D1 and then stretching it out because the cross-section area reduces, but you might also translate that into an increase in velocity. Remember that relationship. They like to provide problems on the AP paper about this. Obviously, when velocity of something is changing, there we go, we have some wonderful things that happen. We know in physics kinetic energy is related to velocity. Suddenly energy increases. What's happening here is a good question. The AP curriculum likes to use this idea and extend it to Bernoulli's principle and Bernoulli's equation. I won't go through the entire derivation, but I will try and give you an idea. Well, hopefully you can intuit it. You might have heard of a tropical cyclone or a depression or a hurricane, and it's often referred to as a low pressure system. But they also talk about winds going at extremely high speeds of 70, 80, 100, 150 kilometers an hour. So higher the speed of that fluid, lesser the pressure. Think of it this way. If you had a bunch of, let's say, monkeys going on in you put them in and they were supposed to walk along a path, and they were just left to their own accord, they were going slowly, they'd probably be fighting with each other, pulling on things on the sides of the path. But for some reason, if you either scared them or motivated them in other means to go fast and forward, they've been marching ahead and they wouldn't really bother each other or anything on the side. So as their speed increased, effectively the pressure that is felt by the road and that system into which they're flowing is less or not. No comments on what's going on inside them. But this is really the observable pressure of the material inside, right? Its pressure actually reduces. Same as if you had one of those strong monsoon windy days and wind was flowing past your window, you would always want to shut your windows because otherwise it tends to pull your window out. Why? It's a low pressure system outside, much higher pressure here. And that's what happens. Now, how do you kind of reconcile this and get the idea with Bernoulli's system? So one of the things you want to keep in mind is energy, right? So velocity increases when you let's say have a pipe like this. I'll just continue this pipe, and somewhere in between I decide to reduce this pipe's some kind of a reduction. I've reduced this pipe into this size. So imagine this: if I was on a road and there were cars coming in and there's road works going on and they suddenly say, okay, slow down now, lanes are... So what happens? Everybody just kind of slows down here, and then there's this massive congestion that pulls back the highway. And as they come out here, people get a sigh of relief, step in the gas, drive out really fast. And then here for like 2 or 3 kilometers, it's all tailback and it's slowly moving in, inching, and then they're trying to juggle and fight here and they get to and speed out. It's somewhat similar to that idea. Of course, if you were planning traffic, you would ask them to slow down here, so they came really slow, and when they got here, you'd ask them to speed up, so then there would be no congestion at all, right? Think about it. If people came in really slow, but right here you told them they had to speed up, they'd start accelerating, and this, if you said this was double the speed, they had to be double the speed, then suddenly everybody would accelerate when they got there. There would be no congestion at all. But water behaves in similar ways, but the opposite intuition. So it comes in here, much higher pressure. Here it's flowing faster, it's lower pressure. But the idea is, if you look at it from energy's perspective and bring the multiple factors together, right? You can just say we have kinetic energy, right? And then we have gravitational potential energy, right? I call it PE, right? I should call it GPE because it's really gravitational potential energy. That's the effect. And if there's a change to that, so there's these two here, there's these two here, but when there's a change to that, right? When energy actually changed, so what might be happening, and work is done, right? So how do I translate this work done into something? Well, I could say W here, and Let me just play with this a little bit just to give you a fundamental sort of view on where we're going. If I say work is done, and work is typically, you could say, force times distance, right? So I could do work as force times distance. I could do force as pressure times area times distance now, right? And if you look at pressure, I did say that there's possibly pressure here, that's pressure 1, and pressure here, assuming these are sort of 2 points that we want to look at it, right? So you could write this as P1 minus P2 times volume, right? So just kind of, again, there is no major mathematics here. This is really, it would be nice to think through and get the intuition behind how this is being worked at, right? Work is done if energy has to change. And the reason why I suggested that the energy has to change is because we saw that there was something happening here that was increasing the speed. And then I said, oh, that means pressure is dropping. Well, I said, let's assume and start with this fundamental idea that, there's kinetic, if it's flowing, there's kinetic and potential energy. If something is happening here, there has to be some work done. Otherwise, energy would not change at all, right? So I'm just using this idea that with the assumption that something is happening. And if I did that, and then on this side, if I manipulated this a little bit, kinetic energy would be on this side, so final minus initial perhaps. Yeah, I could do final minus initial, right? So I would have to do P2 minus P1. So it would be kinetic energy 1/2 m volume velocity final square, and then potential energy would be mass times g times, let's say, h, whatever is the, this column has the height. That's probably a concept I should have said. Let me just go through that right now. Sorry, before I go there. So if I have water here, and remember I said the pressure increases with depth because you get the rho GD function as you go down. So if you were building a dam, and this is where structural engineers have to know fluids, because if you were building a dam and you build a wall like this, the pressure exerted here is way less compared to here. So typically they would structure their walls with much higher depth on this side. And reality, depending on the situation, it might be the other way around because it gets them more support, but usually it's this way. So there is more strength to the wall here than is here. So just a second, just remember this as a old lesson from engineering school, but yeah, that's GH, call it 2, and then subtract half m, the initial velocity, that's the velocity here, I just call it v1 square, subtract m, g, and h1, right? So something like this, if you did this and if you brought volume on this side now, all of that will become density. So I could probably write this whole thing as P1 minus P2 equal to half density times velocity. Should call it final, isn't it? I should call it 2 square plus density G H2 minus minus half rho V1 square and minus half density GH1. I think that should be fine. But if I played around with it and then just sort out my state here and state there, rewrite everything, you could say pressure plus kinetic energy. This is a strange expression of kinetic energy because it's not mass, it's density here. So the volume is addressed there, and gravitational potential energy also is density, should be equal to the P2 plus rho V2 squared plus rho H2. So think of this as a combination where energy is conserved, right? So pressure change can effectively do work, and that work, and if you bring the pressure in and as a factor of the total energy, there is conservation here, and this is really the Bernoulli's sort of equation, and then an extension of this is the fact that when you create a higher, so in airfoils, for example, in the wings of an airplane, you have this situation where you bring air, it flows through a much higher velocity here, V on the top, versus here, where it's V on lower, and this is upper, and therefore the pressure differential here results in a lift. Why? Because in order to accommodate that pressure change, we have to compensate with gravitational potential energy being elevated, so you have to lift it up, and it comes from here. I think this should be fundamentally what they do. I don't think they get into great depths of fluid mechanics or ask you to work on an airfoil. Most likely it will be questions that, say that, hey, the pipe moves here, what happens? But if you have these components correct, then you'll be fine. The only thing I would also suggest to remember is there is the absolute pressure. For example, there is the absolute pressure in the sense the pressure that we feel right now. But if you put in a blood pressure meter on my arm and recorded pressure, and you got, say, whatever, 120 or 80 millimeters, that's gauge pressure. So it's important to understand absolute versus gauge, right? And if you use absolute pressure here, you should use absolute pressure here. If you use gauge pressure, so that might be a tricky area where they might ask you questions where they might give you a reading, and just make sure you don't, on a multiple choice, you don't get confused by something that might be there. If it's absolute pressure, it's absolute pressure you use on both sides. If it's gauge pressure, it's gauge. Sometimes they have a reading, found at this machine, found a reading of so and so, and then just be careful when, especially if it's if it's water and it's the depth of water, then be careful with that pressure, because right at the surface of water, it's absolute pressure. So that's something you have to be careful. Otherwise, I think I've covered most of what the AP fluids part covers: pressure, quantity of flow, the manipulation of volume, area, and such things. Archimedes principle, we talked about it, buoyancy, the force of buoyancy, and here we go, the energy-pressure relationship, which is Bernoulli's equation, and the Bernoulli's principle that results from it. Hopefully I have you covered for AP Physics 1 fluids portion. Rest to follow.